Hi, welcome back to my class in statistics. For today, we will take up measures of variability. These measures of variability are also known as measures of variation or measures of dispersion. After we have located the center of a distribution of data, we now look for indicators of the dispersion of the measurements from a central value such as the mean, or we look for a value that would indicate the the spread of the measurements from a central value such as the mean. And we start with the first measure of variability known as the range. But before that, I would like to point out the importance of obtaining some measures of variability. Like in a production of bolts, if you have a set of bolts with different diameters, or if there is a great variation in the diameters of the bolts produced, then this would imply that there is a high probability of that most of the bolts produced are defective. And another example would be if you want to discriminate between the good performing students and the poor performing students in your class using an examination. But you find out that after you administer the test, there is very little variation in the scores of the students. So this little variation in the scores of the students would imply that the instrument you use your examination to discriminate between good and poor students is not a good instrument, and thus it has to be revised, because with very little variation in the scores of students, it's difficult to discriminate between the good students and the poor students. So we start with the range. The range is defined as the difference between the highest and the lowest measurements or values in a given set of data or measurements. Consider the following distributions of two sets of data represented in a diagram. Consider the following pictorial representations of sets of data. In the horizontal axis, we write the scores or the measurements denoted by X. In the vertical axis, we write the relative frequency, which we have already taken when we took up the frequency distribution table for ungrouped data. And the relative frequency is defined as the relative frequency expresses the H frequency as a percentage of the sample size. In this first graph, the central value is 4. That means the center of the distribution is 4 because 4 is located at the center of this graph or the center of this distribution of measurements or values. In the second set of measurements or values represented by this graph, the center of the distribution is also at 4, or 4 is located at the center of the distribution of measurements. So this set of measurements have the same central value, or their centers are located at the same value or measurement. But by inspection of these two representations of the two distributions, the scores, the measurements in the second distribution of values are more dispersed from the central value 4, while this in this set of measurements represented by this graph, the measurements in this set are centered, or they are close to the central value 4, while the set of measurements in this set, the values are scattered away from, they are scattered away from the central value. So although these two sets of distributions have the same central value, or they have the same, the centers of these two distributions are located at the same value, they have different variation. Now consider these two sets of measurements represented by these two graphs. In this graph, the lowest value is 0 and the highest value is 8. And if you would compute the range of this set of measurements, we said that the range is the difference between the highest and the lowest measurements in a set of measurements or values. Then the range of this set of distribution is 8 minus 0. The highest is 8 minus the lowest is 0, and the range is 8. Also, this for this set of measurement, for this distribution of values or data represented by this graph, the range is also 8. The lowest value is 0 and the highest value is 8. And range is the difference between the highest and the lowest values or measurements. Thus, for this set of data, the range is 8 minus 0, 8. Again, as in these two sets of data, these two sets of data have the same range. But by looking at the graphs of the representations of these two sets of data, there is a difference in the variations among the measurements in each set of data. Although this has a range of 8, the scores are more closer to the central value, while this set of data with the same range of 8, 8 minus 0, the values are dispersed from the central value. So we can say that the range is not a very good indicator or measure of the dispersion of the measurements in a set of measurements. Although we will use later on the range when we present the set of data, when we present data in frequency distribution for group data. We will use the range to calculate the class width of the class intervals in a group data. So the next type of measure of variability or measure of variation or measure of dispersion are the fractals, or also known as quantiles. And today we will take two types of these quantiles or fractals: the quartiles and the percentiles for ungrouped data. The computations of the fractals or quantiles for group data is different from the way we find the quantiles for ungrouped data. For today, we will take the quartiles and percentiles for ungrouped data. But the interpretations of these quantiles for ungrouped and group data are the same. Again, the second type of measure of variation or measure of variability or measure of dispersion are the quantiles or fractals. These quantiles or fractals are numerical values that divide a set of measurements or set of data or set of values into equal parts. And there are three types of quantiles or fractals. The first type is the quartiles. The quartiles divide a set of measurements into 4 equal parts. If we take this line as one whole, the set of measurements, and we want to divide this into 4 equal parts, then you would need 3 cuts on the line. If you want to divide this one whole line into 4 equal parts, you need 3 cuts in order to divide this into 4 equal parts. So we cut the line at this point, and the second cut at this point, and the third cut at this point. And using these 3 points or 3 cuts, we have divided the line into 4 equal parts. And since these are 4 equal parts, this part is 1 out of 4 equal parts. Or this part represents 1/4 of one whole. Also, this is the second of the 4 equal parts, and this is another one of the 4 equal parts. So this part of one whole is called is 1/4 of one whole. And so this third equal part and the fourth equal part, each is 1/4. 1/4 of one whole. So we need 3 points to cut one hole into 4 equal parts. That's why the first set of quantiles is known as quartiles for 4 equal parts. Now these 3 points are known as the quartiles. The first point is the first quartile, denoted by Q sub 1. The second point is the second quartile, denoted by Q2. And the third point is the third quartile, denoted by Q3. These quartiles, Q1, Q2, Q3, are values. They are numerical values. And 1/4 is, if you will convert that to 100%, 1/4 is 25%. So this part represents 25% of one whole. And this, another one of the 4 equal parts, represents another 25% of one whole. And the same with these last two equal parts, they represent 25% of one whole each. Now, with reference to the first quartile, we say that 25% of the measurements from the set of measurements are below the first quartile. The measurements are arranged in ascending order. And with reference to the first quartile, we say that 75% of the set of data or set of measurements are above the first quartile. 75% is 25 plus 25 plus 25%. With reference to the second quartile, we say that 50% of the data or the set of measurements, those to the left of the second quartile, are below the second quartile. 50% because we have 25 plus 25%, 50%. And to the right of the second quartile, those are the measurements that are above the second quartile, and they are 50%, another 50% of the set of measurements, 25% and 25%. So the second quartile is at the middle, exactly at the center of the set of measurements. That's why the second quartile is also equal to the median. You note the second quartile is equal to the median. If you recall, we define median as the center of the distribution of data. It is a value that is located at the center of the distribution of data, and we have considered two cases for finding the median. If the number of values or measurements is odd number, there is exactly one, after you arrange this set of measurements in order, ascending or descending order, you find that there is exactly one value or measurement at the center of the distribution of data. And at most 50% of the set of measurements is below this median, and another at most 50% are above the median. But if the set of values if a set of values or a set of measurements has even number of measurements or values, then there is exactly one value at the center, and it is the mean of the two values located at the center of the set of measurements arranged in ascending or descending order. And for an even set of measurements, exactly 50% are above the median and exactly 50% are below the median. And that's why the second quartile is equal to the median. Also, if you are a teacher or instructor and you make your passing score, you make the median as your passing score. Suppose in a class of students, you get the median of their scores and you make the median as your passing score. Then 50% of your class, 50% of your students will fail. But that is an easy way, an easy method of elimination. If you want to eliminate quickly 50% of your class, then you use the median as your passing score. Now with reference to Q sub 3, the third quartile, 75% of the set of measurements are below the third quartile. Those are the values to the left of the third quartile. 75% is equal to 25 plus 25 plus 25. And to the right of the third quartile, we have 25%. That means 25% or 1/4 of the set of measurements are above the third quartile. The second type of quantiles or fractals are the deciles. Now the deciles, the quartiles divide a set of data into 4 equal parts, while the deciles divide a set of data into 10 equal parts. And the percentiles divide the set of data into 100 equal parts. The percentiles divide the set of data into 100 equal parts. If in quartiles we need 3 points to divide a set of data into 4 equal parts, in deciles we need 9 points. You need 9 points to divide this one whole into 10 equal parts. So if you have 10 equal parts, each part will be 1/10 of one whole. Or each part would be 10% of one whole. For the percentiles, you need 99 points to divide this one whole into 100 equal parts. And if you have 100 equal parts, each part is 1/100 of one whole, or each part would be 1% of one whole. So you see the pattern. The number of points or values to divide a set of data is 1 less than the number of equal parts. If you want 4 equal parts, you need 3 points to divide the set of measurements. If you need 10 equal parts, if you want to divide one whole into 10 equal parts, you need 9 points to divide that one whole into 10 equal parts. And if you want to divide the set of measurements, set of data into 100 equal parts, you need 9 points to obtain 100 equal parts. Thus, again, the number of points or values needed to divide a set of data into equal parts is 1 less than the number of equal parts, or the number of equal parts is 1 more than the number of points needed to divide one whole into equal parts. Now we will take examples for finding the quartiles for ungrouped data. Before we take an example on how to find the quartiles for ungrouped data, we formally define quartiles. The lower quartile, denoted by Q sub 1, or the first quartile, is the value of x such that at most 1/4 of the measurements are less than x, and at most 3/4 are greater than x. As I have illustrated earlier in a diagram, the 25% of the set of values or the set of measurements are below or less than the first quartile or the lower quartile, denoted by Q sub 1. And 75% of the measurements or the values are above or greater than the first quartile or the lower quartile, denoted by Q sub 1. 1/4 here, if you will convert to percentage, is 25%. And in this definition of quartiles, you have to first arrange the given values or the given measurements in some order, either in increasing or decreasing order, or ascending or descending order. Now we define the upper quartile, or Q sub 3. The upper quartile, Q sub 3, is the value of x such that at most 3/4 of the measurements are less than x, and at most 1/4 are greater than x. I have also illustrated this in a diagram earlier. Considering the upper quartile or the third quartile, denoted by Q sub 3, 75% of the set of measurements or values are below or less than the third quartile, and 75% is the same as 3/4. At most 3/4 or 75% of the values or set of measurements are below or less than the third quartile or upper quartile, denoted by Q sub 3. And the other 25% are greater than or above the third quartile or upper quartile, denoted by Q sub 3. Now the middle quartile is the second quartile. And as I said earlier, the second quartile is equal to the median. That means 1/2 or 50% of the set of values or measurements are below or less than the second quartile, denoted by Q sub 2. And the other half or the other 50% of the values or measurements are above or greater than the second quartile or the middle quartile, which is equal to the median. The second quartile, that's Q sub 2, is the value of x. X is a numerical value such that at most 1/2, that's 50% of the measurements are less than x, the value of the second quartile or the middle quartile. And at most 1/2 or 50% are greater than x, the value of the second quartile or the middle quartile. Now this is how we calculate the quartiles. Q sub 1 is in calculating the quartiles for a set of measurements for ungrouped data. data that is not presented in a frequency table using class intervals, that's ungrouped data, you have to first arrange the given set of values or measurements in ascending or descending order. Usually we arrange them in ascending order, that means we start from the lowest value. And the location of the first quartile is the value of x in the position 0.25 multiplied by n plus 1, where n here is the number of measurements or the number of values given, and 0.25 is equal to 1/4, because as we said, 25% or 1/4 of the set of measurements are below or less than the first quartile, whose value is denoted by x. The location of the second quartile, denoted by q sub 2, or the middle quartile, denoted by q sub 2, is the value of x in the position 0.5 multiplied by n plus 1, where n again is the number of values or measurements given, and n plus 1 is multiplied by 0.5, where 0.5 is equal to 1/2. Because as we said, the middle quartile or second quartile q sub 2 divides the distribution into two equal parts. The lower 50%, those are the values that are less than the second quartile. And the upper 50%, those are the values that are greater than the second quartile. The location of the third quartile, is the value of x in the position 0.75 times n plus 1, where n again is the number of values or measurements given, and 0.75 is equal to 3/4, because we know that 3/4 or 0.75 or 75% of the set of values or measurements are less than or below for the third quartile. 3/4 of the measurements are less than. That's why we have 0.75 here. We can write this in a more compact way. Generally, the location of the k quartile, q sub k, is the value of x in the position k over 4, n times n plus 1, where k is 1, 2, 3, because we have 3 quartiles denoted by q1, q2, q3. And n is the number of values or measurements given. Hence, if you want the first quartile, k is 1. Q sub 1 is the value of x in the position. K is 1, 1/4 times n plus 1. But 1/4 is 0.25. If you want the value of the second quartile, then k is 2. You get q sub 2, the second quartile, is the value of x in the position. K is 2, 2 over 4 times n plus 1. But 2 over 4 is equal to 1/2, and 1/2 is 0.5. That's why we have 0.5 here, multiplied by n plus 1. Where n again is the number of values or measurements given. And if you want the value of the third quartile, you take k equals 3. And you have q sub 3 is the value of x in the position. K is 3, 3 over 4 multiplied by n plus 1. And 3/4 is equal to 0.75 multiplied by n plus 1. That's why we have 0.75 times n plus 1 here. Now we take some examples for calculating the 3 quartiles for ungrouped data. For our our first example, consider the following given set of values or measurements. We have 3, 7, 5, 11, 9, 4, 16, and 2. And we will find the first quartile, Q1, the second quartile, Q2, and the third quartile, Q3. This is an example of ungrouped data, not presented in a frequency table with class intervals or classes. The first step is to arrange the given values in ascending order. You start from the lowest up to the highest. So we arrange them from 2, 3, there is 4, first step is to arrange the given values or measurements in ascending order. In this particular set of values, the number of values given is 8. 1, 2, 3, 4, 5, 6, 7, 8. N is 8. As we said earlier, the position of the K quartile, where K is 1, 2, 3, the K quartile is the value in the position K over 4 multiplied by quantity N plus 1, where K is 1, 2, 3 because we have 3 quartiles, and N in our given set of values is 8 because we have 8 values given. We start with Q1. We find the first quartile Q1, 4 Qs of 1, your K is 1. So you compute 1 over 4 For the first quartile Q1, our K is 1. K is 1. And for K is 1, you compute K over 4 times quantity N plus 1. For K is 1, divide by 4, N is 8, the number of values given, plus 1. 8 plus 1 is 9, multiplied by 1 is 9, divide by 4. And you compute 9 over 4, you convert 9 over 4 to decimal number using your calculator. We have 9 divided by 4 is 2.25. Now, how do we interpret this 2.25? You take the largest integer, the largest positive whole number that is less than 2.25, and that largest positive integer or whole number is 2. 2 is the largest positive integer or whole number that is less than 2.25. Now you take the smallest or the lowest positive integer or whole number that is greater than 2.25, and the integer is 3. Again, 3 is the lowest or the smallest positive integer or whole number that is greater than 2.25. Or you find that integers 1 lower than 2.25 and 1 greater than 2.25, such that 2.25 is between these two integers. But the first integer must be the greatest, the largest, the biggest positive integer or whole number that is less than 2.25. And the other integer should be the smallest or the lowest positive integer or whole number that is greater than 2.25. Now, the first quartile, Q1, that we are looking for is between the second Again, the first quartile, the value of Q sub 1 that we are looking for is between the second value in this ordered arrangement of values and the third value in this ordered arrangement of values given. From this arrangement of the values given, the second value is 1, 2, 3. 3 is the second value in this arranged order of measurements or values. And the third value is in this ascending order, ascending arrangement of values, is you count from 2, you count 3, 1, 2, 3, 4 is the third value. This means that the value of Q sub 1, the first quartile, is between 3 and 4, between the second and the third values in this ascending arrangement of values. So the value of Q sub 1 is greater than 3. Q sub 1 is somewhere here, between 3 and 4. The value of Q sub 1 is greater than 3, but less than 4. But our definition of the first quartile says that the location of the first quartile is 1/4. 1/4 of the distance between the second and the third value. So we calculate the value of Q sub 1 as follows. Q sub 1 is greater than 3 and less than 4. And the value of Q sub 1 is 1/4. 1/4 of the distance between these two values. So 3. Why 3? Because Q sub 1 is greater than 3. 3 plus 1/4. 1/4 of the distance between these two values. The distance between these two values is given by the difference of the third value minus the second value, or 4 minus 3. And that's 4 minus 1 is 3. Multiplied by 1/4 is 1/4. And 1/4 is 0.25 plus 3. Hence, the second quartile is 3.25. The value of the first quartile is 3.25, and it is between 3 and 4. Now you can check, we said that at most one-fourth of the values, are below or less than the first quartile. At most one-fourth of the values one-fourth of the number of values, one-fourth of n. And our n is equal to 8. 1/4 multiplied by 8. That's 1 multiplied by 8 is 8, divided by 4 is 2. At most, one-fourth of the values are less than the first quartile, 3.25. So the number of values less than 3.25 is 2 or 1 or 0, because the definition says at most one-fourth of the measurements or the values given are less than or below the first quartile. And you can see that the number of, in this ascending arrangement of values, two values, 2 and 3, are less than the first quartile, 3.25. Therefore, this is correct because this says that one-fourth of the measurements, one-fourth of 8, which is 2, are less than. And you see that there are exactly two values that are less than 3.25. And at most, 3/4 of the values are greater than or above the first quartile. We check that. We calculate 3/4 of n. And our number of values given is 8. And we have 8 divided by 4 is 2, multiplied by 3 is 6. At most, 6 values are greater than 3.25. So the number of values greater than 3.25 can be 6, 5, 4, 3, 2, 1. The maximum is 6. So let us count from this ordered arrangement of values. How many values are greater than 3.25? Q sub 1 is here, 3.25. The number of values greater than 3.25 are 4, 5, 7, 9, 11, 16. And we count 1, 2, 3, 4, 5, 6. And so this is true. The number of values greater than the first quartile, 3.25, is at most 6. The maximum is 6. And it happens that there are exactly 6 values greater than 3.25. And these 6 values represent 3/4 of the set of values of 8 values. Or 75% of 8 is 6 values. These 6 values are 4, 5, 7, 9, 11, 16. Now we calculate the second quartile. Compute the value of the second quartile, or Q sub 2. And you should remember that the K quartile is the value, numerical value in the position K k over 4 times n plus 1. For the second quartile, your k is 2. For k is 2, you compute k over 4 multiplied by quantity n plus 1. We write k is 2 divided by 4. Multiply by quantity n is 8 plus 1. And you use your calculator to compute this. 8 plus 1 is 9, multiplied by 2 is 18. Or 2 over 4 is 1 half. 8 plus 1 is 9, divided by 2 is 4.5. Again, you take the integers that are less than 4.5 and greater than 4.5, but those integers must be closest to 4.5. What is the greatest or the biggest, the largest integer that is less than 4.5, and the largest positive integer or whole number that is less than 4.5 is 4. And you take the smallest or the lowest positive integer or positive whole number that is greater than 4.5, and that integer is 5. 4 and 5 are the integers, positive integers closest to 4.5. You can see 4.5 is between the integer 4 and the integer 5. And this means that the value of the second quartile is between the fourth value and the fifth value. In this arrangement of the 8 values. So from this arrangement of the given values, the fourth value is 1, 2, 3, 4, 5. And the fifth value, 1, 2, 3, 4, 5, is 7. Which means that the value of the second quartile, Q2, is between 5 and 7. Between 5 and 7. And this definition means that 2/4, the value of Q sub 2 or the second quartile is 2 over 4, or that's 1 half. 1 half of the distance between 7 and 5, or 5 and 7. The second quartile is between 5 and 7. It is greater than 5, and 1 half, 2 over 4, or 1 half of the distance between 5 and 7. Thus, the value of the second quartile, is greater than 5. We write 5 plus 2 over 4, or 1 half. 1 half of the distance between 5 and 7. Again, the distance between 5 and 7 is the difference between 5 and 7, but you start with the bigger number or the larger number, 7. 7 minus 5. And we have 7 minus 5 is 2. Multiply by 1 is 2. Divide by 2 is 1. plus 5 is 6. And you can see that 6, the value of the second quartile is exactly between 5 and 7. Now we check the definition of the second quartile. The definition says that at most 1/2 or 50% of the values arranged in order are less than or below the second quartile, or 50% of these values, that's 1/2, are below 6. The definition of the second quartile says that 1/2 or 50% of the values are less than or below the second quartile. So we compute 1/2 of n. 1/2, 8 is the number of values. Multiply by 1/2 is 4. This means that there should be 4 values. At most 4 values are below the second quartile, or at most 4 values are below or less than 6. So we go back to these values arranged in order, and we count how many values are below 6, and there should be at most 4. The greatest number of values less than 6 is 4. And the values less than 6 are 2, 3, 4, 5. And that's how many values? 1, 2, 3, 4. So this is satisfied. There are 4 values, exactly 4 values in this arranged values arranged in order that are less than 6. And the definition of the second quartile also says that the other 50%, or another 1/2 of the set of values, 1/2, the number of values is 8, that's 4. Another 4 of the values given are greater than the second quartile, which means that at most 4 of these values given are greater than 6. So we check that. We count the number of values greater than 6. Those are 7, 9, 11, 6. Hence, this is also true. There are at most 4 values greater than the second quartile 6. And in our data, there are exactly 4 values that are greater than the second quartile. So this is an example of data where the second quartile divides the set of data exactly into 2 equal parts, the lower 50% and the upper 50%. Now we compute the value of the third quartile. We now find the value of the third quartile, denoted by Q sub 3, also known as the upper quartile. Again, you don't forget to remember this definition of the kth quartile. The kth quartile is the value, numerical value in the position k over 4 times quantity n plus 1. For the third quartile, the value of k is 3. And for this value of k, you compute or calculate k over 4 times n plus 1, where k is 3 and n is the number of values given. We compute k is 3, divide by 4 times quantity n plus 1, where n is 8. Now we have to make use of calculator. This is 8 plus 1 is 9. Multiply by 3 is 27. 27 divided by 4. We need to calculate 27 divided by 4. And you get 6.75. Now you take the two integers that are closest to 6.75. One is less than 6.75 and the other is greater than 6.75. And those two integers are 6 and 7. Six is the greatest or the largest integer that is less than 6.75, while 7 is the smallest or the lowest positive integer or whole number that is greater than 6.75. And this means that the value of the third quartile is between the 6th value and the 7th value in this set of values arranged in order. Again, the value of the second quartile or Q sub 3, the value of the third quartile or upper quartile denoted by Q sub 3 is between the 6th value and the 7th value in these values arranged in order. Hence, we find the 6th value. 1, 2, 3, 4, 5, 6. 9 is the 6th value. And the 7th value, 1, 2, 3, 4, 5, 6, 7. The 7th value is 11. Now, what does this mean? This means that the value of the third quartile, Q sub 3, is between 9 and 11. The exact value of Q sub 3 is between 9 and 11. And the value of the third quartile is 3/4. 3/4 of the distance between 9 and 11. Now we find the value of the third quartile. The third quartile is greater than 9. You write 9 plus 3/4. 3/4 of the distance between 9 and 11. The distance between 9 and 11 is given by the difference 11 minus 9. And we compute this using our calculator. We have 11 minus 9 is 2, and multiply by 3, that's 6, and 6 divided by 4, 6 over 4 to the lowest terms is 3 over 2, and 3 divided by 2 is 1.5, plus 9 is 10.5. Again, 11 minus 9 is 2. Multiply by 3 is 6 over 4. 6 over 4 to the lowest terms is 3 over 2. And 3 over 2 is 1.5. Plus 9 is 10.5. So the third quartile, 10.5, is between 9 and 11. 10.5 is between 9 and 11. Now we check the definition of the third quartile. The definition of the third quartile says that at most 3/4 of the measurements or values are below the third quartile, or 3/4 of 8, the number of values, are below or less than 10.5. We now check we calculate 3/4 of the number of values given, because the definition of the third quartile says 3/4 of the values or measurements are below the third quartile of 10.5. 3/4 of the number of measurements or the number of values given, 3/4 of n is equal to 3/4 multiplied by 8, because 8 is the number of values given. And 8 divided by 4 is 2, multiplied by 3 is 6. This means that at most 6 values are less than or below 10.5. So let us check how many values are below or less than 10.5. 1, 2, 3, 4, 5, 6. There are exactly 6 values that are below or less than 10.5. Thus, this is true. At most 6 values are below or less than 10.5. The greatest or the largest number of values less than or below 10.5 is 6. And in our example, there are exactly 6 values that are less than 10.5. Now, the definition of the third quartile also says that the other 25%, 3/4 is 75%. The other 25% or 1/4 of the values are greater than or more than above the third quartile 10.5. So we calculate 1/4 or 25% of the number of values, n, which is 8. And 1/4 of the number of measurements, or 1/4 of 8, the number of values given is 2. 8 divided by 4 is 2. This means there are at most 2 values that are greater than or above 10.5. So let us check how many values are greater than 10.5. 11, 16, that's 2. And so this is satisfied. At most 2 values are greater than or above 10.5. In our example, there are exactly 2 values that are greater than or above the third quartile of 10.5. For your practice, please try the following exercises. Find Q1, Q2, and Q3. In number 1, the given measurements are 13, 7, 3, 8, 12, 17, 6, 10, and 1. And for you to be able to check your answer, I give you the answers. The first quartile to 2 decimal places is 3.75. The second quartile is 8, a whole number. The third quartile is 12.75 to 2 decimal places. In number 2, the given measurements are 3.25, 1.65, 4.21, 2.56, 1.83, and 5.72. And for this exercise, I give you the answers. The first quartile, correct to 3 decimal places, is 1.695. The second quartile to 3 decimal places is 2.905. And the third quartile or the upper quartile is 5.343, correct to 3 decimal places. If you have a question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalisan. Or ask your friends and classmates to subscribe to my YouTube channel, Art Kalisan, the channel of learning and leisure. Thank you for joining me in my class today.